Okay, today what we're going to do is we're going to be talking about section 8.3. Our first objective is we want to be able to construct the confidence interval for the mean. Section 8.2 that we had just gone over was all of the proportions. So today we're going to dive into all of the averages. Okay, so when we're working on finding a confidence interval for the mean, there's two ways that this can be done. The first is when the scenario is that your population standard deviation is known. So if your population standard deviation is known, then we're going to use this formula, okay, x bar, our statistic, plus or minus. We're going to have the same z star critical values as we did for our proportions, all right? And then our standard deviation of our statistic is going to be the sigma over root n, or s over root n that we had, okay, because you're going to have your standard deviation. Well, for this one it would be sigma because our sigma is known. Okay, over here, I just broke it down to be in actual interval notation, right? Like it could be, 5 less than mu less than 7, something like that in the end. This is one way that it can be shown. This is actually the way that I prefer it. You could do the same thing with proportions and put a p in the middle. I prefer this way, but the College Board writes it in like an interval notation with the parentheses, and that's okay too. So if we take a look at example 1, all right, and we'll kind of cruise through this. The average price of 40 recently purchased Moulaville homes, taken via a simple random sample, was $730,000. Assume that the true standard deviation of all home prices is sigma equals 60,000. We want to construct a 95% confidence interval for the true average price of all recently purchased homes in Moulaville. Our process is going to be very similar to what we had in proportions, except this time we're talking about averages. So we're going to have 730 plus or minus. We have these memorized based on how many we practiced in section 8.2. Our z star is going to be 1.96, and then our standard deviation 60,000 over the square root of m, which was 40. So we want the square root of 40. All right, you're going to put this in your calculator for the positive, put this in the calculator for the negative, and then hopefully your answer came up as 711,406.15 up to 748,593.85. Okay, so now let's think about how it's going to be impacted. Okay, that was, we can, like, if we were to interpret it just like we interpreted with proportions, we could say I'm 95% confident that the true average price of all recently purchased homes in Moulaville is between this number and this number. For part B, it's saying now we want to construct a 90% confidence interval for the same data set. And then what do we notice about this interval compared to the 95% confidence interval? So when you're working on this, your x bar is the same, your standard deviation is the same, your sample size is the same. Switching from 95 to 90 is just going to change our critical value. So we would have 1.645 as our critical value. All right, and when you put that in your calculator, all right, and hopefully you've been practicing as you go, you should come up with here. So what happened? All right, what happened to our interval? As we got less confident, right? This was 95% confident up here. This is 90% confident. As we got less confident, what happened to the width of our interval? Okay, this one, the width is narrower. Okay, this is only, what, $30,000 different? And this is $37,000 different. Okay, so the 95% confidence interval is wider than the 90%, where the 90% is narrower than the 95. Be extremely careful. You can't use smaller. Smaller numbers is not the same as a narrower interval. Okay, so it's really important that you use the proper terms to describe them. All right, what's going to change for part C? Construct a 99% confidence interval for the same data. All right, and then let's go back and compare it to our original. So you're going to, 99 means your z star is going to be 2.576. Okay, and when you plug that in, you get those values. Let's look at our 99% confidence interval compared to our, oops, sorry, here's your numbers. Sorry, I didn't see them. So you've got, this is your interval, right? What compared to our original, the 95% back up in part A, now the 99% is wider. Okay, this is $50,000 wide, just about. Okay, so when you think about it that way, the wider the target, the more certain you are you're going to hit it, right? The narrower the target, this one is narrower, the less certain. You're only 90% certain you're going to hit this window, but this is a much wider window, so we can be more confident that we're going to hit it. Now, these kinds of comparisons that I'm making out loud, oops, sorry, and we've talked about them a lot in different ways as we've gone through this lesson, and we'll keep talking about them like this chapter. But you can only really, when you're making these kinds of comparisons, you can only change one thing at a time, right? All the other variables need to remain constant. So I am not manipulating the sample size right now. I'm just talking about if we keep everything the same, what happens if we change the confidence level. All right, now what you need is you need to actually grab this packet, guys. It's your light blue packet. We're going to learn a new table today, okay? And that's going to show up on the next page. All right, objective 2 is we want to be able to locate critical values of t from your t table, and we want to check our conditions for a t distribution. So this important note, I probably should have put stars and bells and whistles on this, right? Okay. We made a major and unrealistic assumption in the example we had just done, now that the population standard deviation was known. It's highly unlikely. If you're collecting sample data and you know your population standard deviation, well, that means that you probably know the data for your entire population. And if you know the data for your entire population, well, then you don't really need to collect a sample, right? So that's really uncommon for what we just did to happen. When you deal with averages, you're almost always going to do what we're about to do now, okay? You're going to almost always know your sample standard deviation is all that's going to be known, okay? And when you do that, you need to use your t distribution. Your t distribution, okay, it's going to be this guy, table B, your t distribution of critical values. All right, and I'll go through this with you, show you how to do it. Is still going to be bell-shaped. It's still going to be symmetric around the mean. It's still going to have your mean, median, motor equal at 0, or all equal to 0, and they're located at the center. It still is never going to touch the x-axis. What's going to be different is that your variation is greater due to substituting s for sigma. If we have a sample standard deviation, we're going to have a greater variation. It's as your sample size gets larger, the area in your t distribution changes and it approaches your normal distribution because s estimates sigma more closely as your sample size increases. What this table is about to give you is there is a different curve for every single sample size. Okay, so when we're looking at this, and you guys will see, let me just make a note before I show you the chart. DF stands for degrees of freedom. For us in this lesson, for the next couple lessons, we're going to have degrees of freedom as always n minus 1. So whatever your sample size is, you subtract 1. And that gives us room to vary with our mistakes and our different things. So you will see right here, degrees of freedom 1. These are the values for the chart where degrees of freedom is 1. These are the values for degrees of freedom 2. This is the chart for degrees of freedom 3. This is the chart for degrees of freedom 4. All right, and it'll carry on. See, these are all their own little charts. You'll notice they're only giving you the positive. You need to use the property of symmetry to know that if you have a negative over here, which we'll deal with a lot in chapter 9, then you would need to just change your t star value to be a negative. All right, you'll notice it's 2 pages. It carries on. All right, if you get to the point where you're in between, technically there are tables out there with every single number. If you're between, you go to the next smallest. You don't go to the closer. So if you have 39 degrees of freedom, you're looking up 30. If you have 58 degrees of freedom, look up 50. Okay? And as we cruise through, what you guys will see is that as it gets to infinity, what we talked about, as your sample size gets larger, your areas get closer and closer and closer to the normal curve. Now, we've been dealing with the same couple numbers, okay? And you'll see here these parentheses, oh my goodness, these percentages at the bottom are the percentages we've been dealing with. We've been dealing with 99%, 95%, and 90%. They're your main guys. And you will see that on here, these are the three that we keep dealing with. So, this infinity sometimes are z-stars. Okay, and sometimes they'll put the z-star right here, that these are the values that you're going to work with. So, if we take a look here, let's just tackle finding your critical values. Okay, so for example 2, suppose that you want to construct a 90% confidence interval for the mean mu of a normal population based on a simple random sample of size 10. What value t-star should you use? So if n is 10, that means your degrees of freedom are going to be 10 minus 1 or 9, and we want 90% confident. You are still going to use the same approach that I had highlighted with you guys when you first learned the normal curve, that if you have 9 degrees of freedom, it's good to put like a separate sheet of paper here as a horizontal to make sure you don't jump lines. We want 90%. You'll notice that it's not here at the bottom on this page, it's on the other guy, right? So you're like, well, how do I figure it out on this side? Well, you'll notice 90% pairs with this number up here, 0.05. Okay, so if you think logically, 90% confidence interval would have 90 in the middle, which would mean 5 in each tail. So this probability up here is the area of each tail. It's not the total of the tails. All right, so whatever notes you need to take on your notes paper, this is the area of each tail. So if we want 9 degrees of freedom and we want 90% confident, that means our tail is going to be 0.05 here. So we're going to have 0.05, 9 degrees of freedom. Our t-star would be 1.833. All right, so what I'd like you guys to do is I'd like you to pause, all right? Try these next 4, A, B, C, D on your own, and then let me know if you have any questions, okay? So as you're cruising through, hopefully you paused. This one would be degrees of freedom 21. We have 98%, which means that each tail, if you need to draw a little sketch to help yourself out, right? 0.98, we'd have 0.01, 0.01. So we would have, in the 0.01 for the area, we would get t-star equals 2.518. Okay, 99% confidence interval. If we have degrees of freedom 12, right, then each tail would be 0.05. All right, and we would get t-star equals 3.055. Number C, letter C, sorry, not number C, letter C. We would have degrees of freedom 6, and we would get 95% confident would mean that each tail is 0.025. So look up the 0.025, connect it with the 6. Our t-star would be 2.447. So if we have degrees of freedom 23, if we look at this curve, if you have 0.92, then that would mean what? We'd have 0.04 here, 0.04 here, and now we've run into a jam, correct? So we've run into a problem because 0.04 is not on our table here. So this is where we can also use our calculator. Just like we have inverse norm, we have an inverse T. So if we go to distributions, here they are, TPDF, TCDF, inverse T. For these, we would be using inverse T, okay? The area, just like when we used inverse norm, still goes from negative infinity up to the line. So for this problem, we would be having 0.04 as the area. And it gives us the degrees of freedom, 23. and our t star. Now they gave me the negative because I did the left tail. I also could have done 0.96, adding these together to get the positive. But really, it doesn't matter. I just always write the positive because the formula will take care of the positive and the negative. Because the formula for like doing your interval, it's going to be x bar plus or minus t star, and it'll be standard deviation over root n. Okay, that's eventually where we're going to head, where these t stars are going to get plugged in right here for this t star amount. Okay, so your critical value, it is crucial. If you aren't told the population standard deviation, or you can't calculate it on your own, you have to use the t distribution. Now, just like everything else, we need to know if we can use the t distribution. Okay, just like when we learned averages in chapter 7 with sampling distributions, we had to first ask ourselves, can we use the normal distribution? Now we need to know, can we use the t distribution? Okay, so we have random, just like last time. Okay, in section 8.2, our conditions that we need to check for a confidence interval about the mean is first, was our data collected randomly? We also need to check our 10% condition. We need to check, is our population at least 10 times our sample size? Whatever notes you need to make, this lets us use the formula for the standard error of the statistic, just like with proportions. This is your standard error of your statistic. Okay, it's your sample standard deviation. Just like right here, I just wrote, this is your sample standard deviation. Okay. We also need to check our large counts, or if we can use the normal approximation. So if your population has a normal distribution, or your sample size is greater than 30, then you're good to go. Okay, you're allowed to use this t distribution to figure out your information. Okay, you can just say sample size is greater than 30, okay to use t procedures. Or I was told the population is normal, so it's okay to use the t procedures, but you have to state that. All right, if you don't know the shape of your population and your sample size is less than 30, then you need to make a little graph. You either need to graph it with a dot plot or graph it with a histogram. Yeah, you have to sketch it as part of your answer, okay? But you need to have that graph because you need to see if it is strongly skewed. If your sample size is less than 30 and you have strong skewness or strong outliers, then you're not supposed to use the t procedures. We'll talk later about what you would use, but we would just go through, can you use it or not? So we're going to rock through these couple problems here. First, we want to determine if we can safely use a t-star critical value. That's it. We're just seeing, can we go through them? Okay, so I'm really just checking here my large counts, because you should be pros at 10% condition by this point. So your large counts check here, right? We want to estimate the average time in minutes in order to receive a regular cup of coffee at a local coffee shop. The time for 5 randomly selected visits to a coffee shop are shown in the dot plot below. So sample size is not greater than 30. It's only 5. So if n is 5, we need to see our graph, which we are already given, if there's strong skewness or outliers. We definitely have an outlier, okay, a strong outlier. So no, we can't use t procedures, or t star you could say, because n equals 5 is too small and there is a possible outlier. It would be okay if n is small and there were no outliers, but if n is small, then you can't have outliers. Okay. For B, we want to estimate the average height of high school students. The box plot below shows the distribution of heights in centimeters for 100 randomly selected students. So can we use this? Right? We've got n. N is 100. So yes, even though there are outliers, the sample is large enough use T-star. All right, n is greater than or equal to 30. And then part C, a middle school counselor wants to estimate how many minutes on average students spend doing homework. A histogram of the amount of time doing homework the previous evening for a random sample of 20 students is shown below. Okay, so n is 20. Does that mean automatically we're out? No, it does not. Okay, I'm going to say that the answer is yes. Although the n equals 20 is small, right? It's less than 30. There is no strong skewness. Or outliers. So it's okay to use T-star. Alrighty. Next lesson, I will teach you guys how to actually do the whole interval. Okay, we'll put it all together. We will talk next class about more of this stuff right here. Good job today. Way to take excellent notes.